So this is, I mean, this talk today is something I've been working on, I think, for about 3 years or so, together with John, who's sitting over here, who answers all the hard questions, and also with Chris Ladrzinski, and various other people have joined in sort of follow-up projects to it. It's a really very simple idea. Its motivation is very strongly linked to heavy tails, and it's very, very strongly linked to sort of how do we construct robust MCMC type algorithms in those kind of contexts. So that was really sort of our motivation, and there's three quite sort of simple ideas to do this. John says this is his favorite photo of himself. Looks very relaxed, and Chris. This paper is hopefully going to be accepted relatively quite soon, and we have various other things going on, but I'll really just be talking about work in this particular paper. Okay, so I think most of you, well, all of you will know about these basic things, but this is really just for kind of orientation. We talk about MCMC algorithms. One of the big problems about MCMC algorithms, we generally construct them on R to the D. R to the D does have this kind of intrinsic problem that algorithms have this kind of transient phase, and what do we do with the transient phase? And people argue for many, many years about what we should do with the output from the transient phase, or detecting the transient phase, or all sorts of things. But in particular, mathematically, you know, how quickly do you actually converge to the sort of stationary phase is something which is obviously not very easy to assess, either empirically or mathematically. And we'd rather do without it. And another problem, which is very important, is that actually very often modern MCMC algorithms, ones involving computing gradients and having to do bounds on various kind of quantities, actually this part of the trajectory is disproportionately expensive to implement. Okay, and that can be a real problem, especially since you're going to throw it all away anyway. So you'd rather not have that. Of course, when we're talking about the stationary phase, again, there are sort of all sorts of issues, ways of assessing how good your Markov chain is mathematically or empirically, and you might want to have algorithms which are as efficient as possible. Now, and of course, so what we often do when we've got heavy tails is we think about the transformations. We do transformations of the state space in order to make things light-tailed, problem solved. Well, not necessarily, because when you're in high dimensions, how on earth do you do that? There are many ways of doing that, and most ways are wrong, and will give you problems in other kind of ways. So this is the stereographic projection is just one way of doing a transformation. But I will try and argue that it's sort of intrinsically a natural, not necessarily the best, but a natural way of doing things, which has some really quite nice positive properties, and also some nice robustness properties in the sense that you can't necessarily make things work. I think one thing that's noticeable about a lot of the transformation methods out there in the literature is that very often they can make your MCMC method much worse than it was to start off with. So that's kind of where we are, and I think you probably all know sort of the that story. So this is the sort of thing I'm going to go through. I'm actually going to talk about two algorithms. Random Metropolis is the very oldest MCMC algorithm in the book, and I'm going to talk about the bouncy particle sampler, which some of you may not know anything about. So I will give a sort of 3 or 4 minute introduction into this particular algorithm. And these are algorithms which are generally defined and constructed in the Euclidean space, and then we're going to look at stereographic versions of those algorithms. Much of the sort of later work which we're going on to, which I won't talk about today, is work which basically allows you to look at other kind of classes of models, other classes of kind of algorithms for which you can do this. But these are going to be our sort of 2 test cases. And even for those 2 very simple test cases, I think that some of the results are really quite interesting. Okay, yeah, so that's basically what we're going to try and get through some of that. Okay, so this is just for orientation. Again, you all know this random Metropolis. I'm just going to look at the simple random Metropolis algorithm. X is our current state. We propose a new state, accept with a probability, and if we accept, then great. If we don't, then we stay where we are. And again, the sort of properties of this are really very well known. I'll go through them later on. a little bit to the things that we might want to improve on. Actually, the random walk metropolis has rather nice properties in some sense in heavy tail context. It has a kind of quite robust properties. It's not quick or anything. It's a negative story overall, but it's actually often no worse, and sometimes even better than some gradient-based algorithms. Okay, and one of the nice properties of it is that if you look at this sort of optimal scale, here's a random metropolis of which basically I've got sort of a sort of roughly optimal proposed scaling H on the right-hand pane, and then the other ones, this one's too small, this one's too big. One of the very nice properties of random walk metropolis, which is kind of unusual compared to things like gradient-based algorithms, is that what's optimal in the stationary regime is actually not optimal in the tails for most algorithms, but it more or less is for random walk metropolis. In other words, if you do what's good in the middle in the tails, it's going to be doing more or less as good as you possibly could do for random metropolis. So this is a nice robustness property that this algorithm has. But overall, it's pretty bad because if you've got a heavy tail distribution, you've got too much mass at infinity, you're not going to come out any better than geometric and polynomially quick, and it could be slightly worse than that. And I'll say something more about that.
So, Gareth, like this, these properties, you know, this robustness properties, good, bad, good, okay. Like, is there a paper that actually, you know, makes those statements precise and
yes,
just?
But I mean, you know, we can't prove it for every distribution, I think, but we can do it for
Family, that is reason.
So what we actually prove it for is sequences of Gaussian density. Oh, it doesn't have to be Gaussian, unimodal densities, which go to in as dimension goes to infinity.
And is that is in that 2022?
Sorry.
Okay.
Oh, no, this is old. This is old.
This is the high dimensional.
It's this high, yeah. So it's basically it's a fluid limit. It's one of the first fluid limit packages for MCMC, basically, where you can look at fluid. You can look at. I can tell you more detail about it
later. Okay.
Basically, the fluid limit story. You can try and optimize your fluid limit, and then you get to a scaling problem, and then you can relate that scaling problem to what the scaling problem is in stationarity, which is a diffusion optimization.
Okay.
And they're both pretty close. But I think by accident, and it's a nice accident. Okay. Anyway, right. So PDMP. So who knows about piecewise deterministic Markov processes in MCMC? Okay, so maybe so about half of you. So I will sort of whiz through this, but it's sort of something I think is kind of exciting in MCMC these days. It's continuous time MCMC algorithm and non-reversible. Okay, what is a piecewise deterministic Markov process? Is what it says on the can. Basically, what you do is you have deterministic dynamics, and this is the general form of it. And then at some sort of Poisson event rate, which is state dependent, the rate is state dependent, you basically jump to some other configuration. Okay, and what do these things look like? Well, this is an example of a PDMP, which I just drew. They're not necessarily as kind of strange as this. This one has a property that it's started here and went to here and then jumped to here. This one has a property that's discontinuous. The ones used in MCMC are actually typically not discontinuous, but they have discontinuous derivative. Okay, so this is an example of a PDMP, and people are very interested in these things partly because they're non-reversible. Well, that's not the only reason, but the non-reversibility is very attractive because of the idea that momentum can kind of get you around the space a bit quicker, and there is a lot of theory developing about PDMPs and how it can have actually distinct advantages in high dimensions over more standard reversible algorithms. But I'm not going to talk about that today, really. But so that's some sort of connections. If anyone wants to read about it, I mean, it really goes back a long way. But these processes have not been studied anything like as much diffusions, but seem to have sort of become much more prominent, not just in simulation, but sort of particularly in simulation cases. Okay. Okay, and so why should we look at non-reversible algorithms? Well, there's various kind of reasons why you might want to do it. I mean, because there's quite a lot of theory which has been around for quite a long time now, which has said things like, wouldn't it be nice if we had non-reversible MCMC algorithms? Because actually non-reversible Markov chains very often have better conversion properties than their reversible counterparts. But of course, mathematically, they're difficult to handle. And also practically, sort of finding practical versions of non-reversible MCMC has been a big challenge. And the most successful one, even ironically, the way it's implemented in its basic form is actually reversible, is Hamiltonian MCMC, which basically has a sort of non-reversible character. Okay, so this is just basically one of the main reasons why you might want to construct algorithms on the basis of PDMPs. And what's the intuition? The intuition is that basically, here's two equals kind of scaling component. The black path here is a non-reversible one. The red one is a reversible one. It's just a simple idea of momentum. Okay, and so there is at least some intuitively there must be some hope that this black one can get you around the space and better than the red one. So this is the main sort of intuition about why PDMPs might be a good idea in simulation. The PDMPs which are used in MCMC have a really, I think, another very exciting advantage over their non-reversible counterparts, which is that they allow you to do principal subsampling. We've had talks about stochastic gradient methods today, and there'll be more during the week. And the point about stochastic gradient is that it will produce stochasticity, which of course, if you do that in the context of a sampling situation, if you do that in an arbitrary way, will induce a bias to your invariant distribution. But PDMPs have a magical property that if you actually do subsampling of your data to massively speed up your algorithms, you actually don't change the invariant distribution. So it has this, what I call principal subsampling, which means that this implementation cost of these things can be very, very cheap compared to the counterparts, even though it's a bit more complicated, but you just don't need to actually compute pi at every iteration. And in fact, the subsamples can be a size 1. They don't even have to be reasonably large. So that's these are some reasons why people are excited about these. So this is one-dimensional, just to give you a picture. This is the trajectory of two one-dimensional zigzag processes. What they do is they go up and they come down. When they go up, basically, and then there's a switching rate which tells them to come down because the gradient is actually telling you it wants to come back. And then it just looks like this. So this is a Gaussian, this is a Cauchy, more heavy tail distribution. Right? And you can sort of see from the more heavy tailed one here that there is an issue about excursions here. So Miha's beautiful talk just before, he was talking about sort of connections between excursions and stability of excursions and rates of convergence. And this is a pretty well understood problem now, the kind of excursion properties of PDMPs and how they link to rates of convergence. In fact, in many ways, this is an easier problem to solve for PDMPs than it is the diffusion-based algorithms like. Okay, so what do these things look like in multi-dimensions? Here's the two-dimensional one. You basically, this simple case here, I've got two velocities, one for the x direction, one for the y direction. Each velocity is plus or minus 1. So you get trajectories that look a little bit like this. Okay, and you can imagine what will happen in high dimension. You're just going to get basically 2 to the d possible directions, and this is how things work. And there are all sorts of interesting questions about how you implement these things and how you optimize them and things like this, but I'm not going to talk about that now. Anyway, so this is going to be my kind of second base algorithm, which I'm then going to sort of lift up to the stereographic kind of context. Any questions about that before we go? Okay, so yeah, so too much about this. Well, basically, this is a genuinely continuous time MCMC algorithm in the sense that you can't just take these points at which you basically change direction. That will give you a biased sample. you actually have to sort of do some kind of post-processing of this and maybe have something like sort of equally spaced time that you could do something of that kind if you want to get unbiased estimators from this. But that's something. Okay. Oh, and then the other thing that you can do with PDMPs, you have a lot of flexibility. So this sort of what I've been describing so far is like a canonical version of PDMP, which sort of minimizes the rate at which you do these kind of switches. It turns out you can actually add on an arbitrary function of your current state for your switching. In other words, you can add an arbitrary amount of extra switches, as long as that arbitrary switching rate is only a function of X and is not a function of V. Okay. So in other words, basically, if I have this lambda I0 is the switching rate for any, or in this case, the canonical PDMP or zigzag process, then I can basically add on an arbitrary function here, and that will still retain exactly the right invariant distribution. What does that do? This essentially gives me sort of more randomness in changing the direction. Okay, so there are very nice results which say that as you let nu go to infinity, this thing starts to look more like diffusion. And so you can appropriately approximate diffusion by that. Okay, so this canonical zigzag is the one that has the minimum possible value of lambda I, has some claim to be the most reversible, and there's some very nice theory by these guys here, which basically gives a precise statement about the advantages that gives you in terms of asymptotic Monte Carlo variances. But I guess what that really is telling you is, in some sense, if you're going to implement one of these things, you want this to be as small as possible. Okay. And so actually, so this is the most kind of commonly used and some generic sampler, which is this one which essentially works in the following way. Imagine these are the contours of your distribution. And what you'll do is you'll have some jump rate, which I haven't written. Oh, it is written down there. Maximum of 0, and this inner product here between the sort of, basically, I look at the direction I'm currently going in and see how steep it is, how steeply I'm going downhill. And depending on how steeply I'm going downhill, if it's steeper, I'm going to change direction more rapidly. And then what you do for this canonical BPS algorithm is you basically reflect in the contour that you're currently in. So this is the way this algorithm is constructed. Very nice, good, simple algorithm. And this is the algorithm, this is specifically the algorithm that we can actually put in stereographic context. Okay. It's a very nice algorithm, but it actually has some quite weird properties. And this is one of the weird properties that it has because of this bouncy property. It has some quite unusual reducibility properties. So this is a trajectory of a bouncy particle sampler for a density which is spherically symmetric. So this circle here is one of its constants. It basically can't, from this starting value here and this velocity, it cannot get inside the circle. So you get a really very extreme version of reducibility. The number of reducible components in this Markov chain is actually uncountably everything, which makes it very nasty. Okay. Okay, so that's something you have to worry about. How do you solve that? Well, you can solve that by doing kind of introducing a bit of extra refresh where you just change your direction at random, as we looked at in the previous thing. So that can actually solve this problem, and that can be quite good. Here's a more high dimensional thing, and it shows the sort of issues that, I mean, it turns out that you can study high dimensional PDMPs and you can actually study what happens. And it turns out that these boundary particle samplers have some really weird properties. They tend to sort of hug to these contours, which are a little bit like the diagram we've just basically looked at. And essentially, to get away from that, you need to introduce refresh. So this is a no refresh version, and this is a refresh version. And one of the interesting questions is, how on earth do we optimize the amount of refresh. And I've written 89% now, which is actually correct. I meant to write 78. My fingers must have been just the right way. 78 was the is the amount that we based in this study on the Gaussian case. Although, yeah, I mean, to what extent that generalizes, I have no idea. Okay, right. So I want to go on anyway. So it's very simple things that we, there are many reasons why we should worry about properties for heavy tail targets. Many reasons why we might want many theoretical properties we might want to ensure. But I'm going to talk about the very basic ones here. What might we want? So things like existence of CLTs, which I'm not going to explicitly talk about today, although they'll be implicit. Geometric ergodicity statements of this, where the total variation distance can actually depend on the starting value, and uniform ergodicity, which is this. And of course, there are actually not very many MCMC algorithms around in Euclidean spaces, certainly on the infinite space, that where we expect to have uniform ergodicity, at least in general. I mean, things like random walk intrinsically don't lend themselves to this. But anyway, we'd like to get these properties if we possibly can, because lots of things follow from them in terms of robustness and reliability of estimation and central limit theorems and all these kind of things can kind of follow from this, right? What also we'd like to know, obviously we'd like to optimize these constants rho and c and all these kind of things if possible, but the very basic, we want to have some properties of this kind. And why we're here today, this week for this conference, for heavy tail targets, these things are basically not, you generally will not get these things. In fact, intrinsically, both the algorithms I've been talking about, the bouncy particle sampler and the random walk metropolis, intrinsically for heavy tail targets, these properties will automatically fail in every single case if you have a distribution with unbounded support. Okay, so this is what happens. This is really well a long time ago. So random walk metropolis is not uniformly ergodic if the support I is R to the D. So Richard Tweedy's first important contribution to MCMC was this statement, and basically, and actually not only that, so we can't get uniform ergodicity in most cases, but actually whenever we have a heavy tail target, then basically we don't have geometry. We say much more subtle results. We have talked about those earlier, but what we're about in this talk is how we actually provide methodology that tries to restore at least one of these. Now, the story with BPF is actually slightly disappointing in that we get the same thing happening. We don't get geometric ergodicity for any heavy tail target distribution. So Georgios Varoustakis did a very nice PhD at Warwick on this topic and some sort of solutions to the problem. And interestingly enough, actually, if you do a direct comparison between the random walk metropolis and BPS, actually BPS does better. You get better polynomial rates of convergence than you do for the random walk metropolis algorithm. But neither of them sort of score highly in some sense because neither of them actually get you to a situation of having geometric ergodicity. Both of them are. Okay, and we picked on these two things. All of these off-the-shelf algorithms that we sort of generally use have exactly the same issues. Oh yeah, and so this is an important thing about, in particular, about BPS. So we can be in the situation where actually not only you have sort of double trouble in that not only are these things slow mathematically, but actually, since they're continuous time algorithms, their implementation costs may not be sort of sort of constant in terms of where you are in the space, and it's quite common for this to be disproportionately computationally expensive in the tail. So not only do you have very slow algorithm mathematically, but implementation costs are pretty large. So there's many reasons why you might want to sort of eliminate this sort of transient. Okay. All right. So stereographic projection. you've probably all seen it in some form. Very simple idea. Diagram on the left-hand side just shows how you can construct it in one dimension. What you do is you basically put a sphere or a circle in this case, you sit it on the real line, and what you do is you project every point onto the North Pole. Okay? And so what that basically, therefore, you identify this point here with this point on the circle stroke sphere. And of course, you can do everything in R to the D just very easily. Now, the formulae for doing this are, I would say, sort of school level algebra. Doesn't mean to say we can all do it. I got it wrong about 10 times before. But actually, it's the formulae that allow you to do this are very straightforward once you do it. And so therefore, in some sense, it's quite easy to go between these two representations. Well, why might we do this? Well, of course, spheres are compact. Well, maybe you're not quite mapping this onto a compact space because you're actually not mapping any point onto the North Pole. You're mapping it onto a pre-compact space. And so therefore, the North Pole here is actually going to play a pretty important role. So if you have pathologies happening at the North Pole, it will be something which will affect you. So we need to take a close look at what's happening. Okay, so, what's the big picture idea? I'm going to be basically getting my distribution. I'm going to get your, which is on use this Euclidean space, which is the flat space. I'm going to be mapping it onto my hypersphere. I'm going to be carrying out an algorithm on the hypersphere. And then if I'm interested in doing some estimation, I can project it back onto the space. It's as simple as that. Okay. So I'm going to try and just give you some sort of ideas for what we might, why this is not such a stupid idea. First of all, constant curvature is actually really useful. I mean, basically there's lots of clever ways in which you might actually want to map a Euclidean space onto a complex manifold. But if you don't have a constant curvature, it's actually going to be quite complicated to construct algorithms in a reasonable way. So this helps a lot. So then there's this really nice kind of idea, which I call the blessing of dimensionality, which I mean, one way of looking at it is from a very nice paper of Alex's from 2018, where he looks at Brownian motion on the surface of a d-dimensional hypersphere, and you find it actually gets quicker and quicker and quicker. As dimension increases, things get quicker and quicker and quicker. And so this is a sort of blessing of dimensionality as opposed to the curse of dimensionality. There's quite a lot of intuition into what's really happening here. I mean, if D is large, where is all the mass? Here's your hypersphere. Imagine this is d-dimensional. Well, if D is large, well, basically all the mass is really at the equator. Right? So all the mass is really at the equator. And if you're starting, say, at the North Pole, which is the worst possible place if you're moving to the equator, actually, if you're in D dimensions, then you've got D Brownian motions, which are all your friend. They're all pushing you in the right direction. So in some sense, Brownian motion, all these Brownian motions are pushing you towards the equator. Once I arrive at the equator, I basically got a uniform distribution because of where I started. And therefore, in some sense, you're in stationarity. So the sort of intuitive idea is that basically this is actually giving you much more rapid convergence than in smaller dimensions. Okay, so there's a number of things about, so therefore, if we can do a projection onto the hypersphere, okay, it's not going to be a uniform distribution. Brownian motion has a distribution that has a uniform distribution on the sphere as its invariant distribution. But if we project onto the sphere, well, maybe we can actually get some of those nice properties. Well, what properties will we want to have? Well, in particular, one thing we'd like to have is for when I do this projection, I'd like most of the mass to be not that far from the equator. Why? Well, because essentially, Brownian motion is basically, it has its own natural invariant distribution, everything mapped around the equator. Therefore, if we project everything onto somewhere around, so maybe the United Kingdom up here in the north, then actually basically Brownian motion. And why am I talking about Brownian motion? Because algorithms like random walk metropolis behave like Brownian motion. They behave like diffusions. Locally, they behave like diffusions. And therefore, if I'm projecting all my mass onto the United Kingdom up here in the north, then my algorithm is pushing me down towards the south, towards the equator. So that's not likely to work well. So I need to be able to do this in some way such that I kind of get things around the equator as much as possible. Okay, right. So that's just some intuition. For anyone who's interested, there is a connection with the polar slice sampler, which is a paper which I wrote a long time ago with Jeff Rosenthal, which is another algorithm which in some sense intrinsically beats the cursor dimensionality. What's the catch? The catch is you can't implement algorithms like this, but algorithms like this should be good ways of motivating how we should be constructing our algorithms. I don't do it on Euclidean space. Okay, so random walk metropolis stereographic is very straightforward. What I do is I basically draw my tangent space. I make a move in the tangent space, and then I project back onto the sphere. It's the most obvious thing you could do. Actually, there are some choices, other things you might do. One thing that's interesting about this is that, if we go, a large distance along this line, it's still going to basically, it's not going to move you all the way around. It's just going to, both going to jump to somewhere like, where is it going to go? It's going to jump to this point here. Right, so it turns out that basically it's kind of controlling the tails in a natural way, and there is a sense in which what we're doing here is actually producing kind of if I do a random walk with an unbounded proposal on this tangent space and I map it back down on Euclidean space, I'm actually using a heavy tail proposal, which I think that relates to sort of some of the talks that we're having. We know the advantages that can actually do. Okay, so that's how that algorithm works. I won't go through the pseudocode. Now, stereographic bouncy particle sampler. Again, I'm not going to go through the pseudocode with you, but just to show you two trajectories. This is basically what I've done here is I've constructed the bouncy particle sampler on great circles on the hypersphere. And if you map those great circles back onto Euclidean space, I can't remember what the distribution here, maybe in Gauss's, then interestingly, if you don't use any refresh, you still get this kind of ball patch in the middle there, where you don't visit. So you do get reducibility issue. If you use refresh, then you get things which actually solve this problem. And there's open questions as to how much refresh you should basically use. Code. Right. So what are the results? I mean, this is the, I guess, this kind of simplest result, but I think it's kind of nice in that it's kind of clean cut. And what it says is basically, I look at the original density, as long as it's not more heavy-tailed than this thing, this basically a T distribution with D degrees of freedom, then I'm going to get uniform ergodicity. Okay, and if I get uniform ergodicity, and if I don't get uniform ergodicity, in other words, when this condition fails, in other words, when I have an even heavier tail distribution, then what happens? Well, something interesting happens that you don't even get geometric ergodicity. So you get this dichotomy between uniform ergodicity or absent. You don't even get geometric ergodicity. So this is the sort of best, easy to show that this is the best possible. Why? I mean, this is, as I said, this is the easiest of all results, and the reason it's easy is because all this is really doing. This term here is the Jacobian when I do the transformation. So all this is really doing is it's actually saying, is the density on the sphere bounded? Because if you've got too much mass in the tail, then your density at the North Pole is actually going to explode. And if a density of any random Warp metropolis, random Warp metropolis on any density which is not locally bounded is not going to be geometrically ergodic by well-known kind of classical results. Okay, so all this is basically saying, yeah, okay, if you do the stereographic projection, as long as the mass doesn't gang up on you at the North Pole, everything's fine. And you get uniform ergodicity. But this is obviously a limited result in some sense, in that if you do have heavier tails, then you know you do have problems. And of course, there's other algorithms you can try and construct. That's another story. What about the bouncy particle sampler? It has slightly better properties. Okay, so it has slightly better properties by half a degree of freedom. And this, we believe, is actually not the best possible result. We think this is close to the best possible result. And this is all related to, so you have some quite interesting things happening here where you have these degrees of freedom around D. So you can have situations where the density could actually blow up. And you can have, very naturally, you can have non-Harris recurrent Markov chains coming up. And what do I mean by that? If you're not used to that sort of terminology, it means that there's some very unfortunate collection of starting values which have measure zero under your stationary distribution, such that if you start at those, then you can basically do something horrible. And in this case, these bad starting values are the ones where you basically start on a collision course with the North Pole. And if that happens, and if you actually get to the North Pole, you can just stick there. So that can happen, but you can still perfectly well have kind of ergodicity from everywhere else. Okay, so and this is just to show some nice results. I mean, this is the random metropolis for on a spherically symmetric density. You get amazing properties for this. So these algorithms. So basically, this is the random metropolis algorithm, and these are the corresponding Euclidean so you get these nice properties. So if you have very nice stylized examples, everything works very nicely. But there's a problem. Well, I say a problem, but there's definitely a big limitation. So basically, one thing that I didn't say at the beginning was that when we construct this sphere, we have choices, right? One choice is, where do we position the sphere? Okay, I'm going to get a different projection if we put it here or if we put it over here. And the other is, how big is that sphere going to be? Okay. And so it turns out that this is basically some measure of efficiency. And if I look at this measure of efficiency, it turns out that the optimal thing to take in this context is basically root D, the radius. And if I take it to be less than this, then actually the efficiency, you see these numbers here are going much lower than the numbers when it's 0.9. So you have this high sensitivity to basically having the right size of sphere. So this means that this algorithm lends itself very, very naturally to adaptive MCMs. Got a massive amount to learn here and to gain from these kind of algorithms. So what's happening here? So here, where you have a sphere that's too small, you just picture what's actually happening here. Basically, what you're doing is you're putting all the mass in the North Pole. And if you're putting all the mass in the North Pole, this algorithm's not really helping. It turns out that so it's a very nice sort of defensive result. Well, not so exciting in a positive way, but it turns out that you can't make matters worse, because the worst case scenario is actually not that you make everything into the United Kingdom, but you make everything into a small island like Christmas Island or something, right? So everything is mapped into a very, very small area. But if you go to Christmas Island, it's pretty flat. I've never been there. I hope you have not mountains, but you know what I mean. It's sort of, the Earth's curvature is irrelevant when you go to an island of that kind. And so therefore, if you do that sort of map and then you actually carry out a random walk metropolis algorithm, you're basically going to behave as if you were in Euclidean space. So you lose nothing, right? So in that sort of scenario, you basically don't sort of lose anything. Right, how long have I got, Simon?
Oh, a few minutes.
A few minutes,
Yeah,
okay.
yeah.
All right,
It's 5 to.
okay, thank you. Right, okay, so let's see what I've got. So I wanted to, maybe I'll just try and give you this result. So this is a result which is a way of talking about this is the random walk metropolis case. And in the random walk metropolis case, we can talk about a diffusion limit result for infinite dimensional random walk metropolis or stereographic random walk metropolis, and comparing the speed measures of those diffusions. And I can compare the two algorithms, one algorithm being the stereographic and one being the non-stereographic. And it turns out that the stereographic is always better. And it's always get better by an amount that I call gain. And gain is 1/1 minus ABC. So basically what's happening here is I've got these three quantities A, B, and C, and they all encapsulate what the limitations of this approach actually are. Okay, so all these constants A, B, and C are less than 1. So I would ideally want them all to be equal to 1, because if we're all equal to 1, then my gain is infinite. And that's exactly what you get if you can actually transform your target distribution to the uniform distribution on the sphere. We see Alex's blessing dimensionality in the case where A equals B equals 1. But what are these things? Well, so this is a situation. So this is a one-dimensional Gaussian distribution with a density F. Okay, so this is expected. And I should say, and a variance 1. So if I look at this quantity, then it's easy to see that this has to be less than or equal to 1, and is equal to 1 if and only if this is Gaussian. Okay, so this is the measure of, actually it turns out to be really a measure of spherical symmetry. B is a measure of, well, basically mu is essentially the, if I place my sphere at the origin and the mean of the original distribution is at mu, then that's suboptimal because I've got it in the wrong place. And so I lose another quantity here. So if in the ideal case, I will basically put my sphere directly over the mean of the distribution. Again, something we might want to learn adaptively. Okay, and then the third way in which we can lose is this constant lambda, and this is to do with the variance of the sphere, which turned out to be this, sorry, the radius of the sphere. And so this is the quantity that you basically get. So the optimal algorithm here will be the one that tries to set A, B, and C as close as possible to 1. And that's something you can try and do adaptively, certainly in terms of changing B and C. But if any of these are actually a long way from 1, then the advantage is actually going to be less than 1. Okay. Right, so I'm probably, I need to finish, right? Okay. Right, so there's a few other things which I haven't talked about, but probably that's fine. I've introduced today stereographic algorithms. Nice points are that I get for really quite cheaply some uniform logistic results, some nice kind of some amazing properties for distributions which are probably not realistic but motivate things that might actually happen for other distributions. I basically have, what else do I have? Well, I should emphasize that computationally these things are easy to implement. And the defensive results basically are that essentially if you do this, you're not losing anything. And then finally, we're working on various kind of extensions of this, adaptive versions, which are very much, adaptive MCMC is, quite old and it's quite established now. But definitely for this class of algorithms, it seems like the potential advantage gains here are going to be really huge compared to things like adaptive random walk metropolis, for which you can gain a little bit, but maybe not huge amounts very often. There's also more sophisticated and complicated and exotic things that we've been trying to do, which I won't sort of go into in any detail unless in all those slides. Thank you very much.
Any questions? Thank you, Gareth.
So you talk about this optimizing R, the design of that, so that you can basically like try to put as much as you can in the equator, right? I mean, that's the intuition. Is like you want to sort of make it in such a way that this happens, and these three ABC criteria that you have, this criteria comes from a limited set of models that.
So this is a situation that I didn't really say clearly. So yeah, it's a good question, Jack. So the target distribution here is the product of independent components, each of them having univariate density M. So it's exactly the context in which you can do these infinite limit things and just look at, the best speed function of each diffusion, and then look at the ratio between the two. And what I'm doing is I'm looking at the ratio between those two. So that quantity here, which is really a measure of how far you are away from Gaussianity, it's not really that, because in the context of this artificial experiment, Gaussian is the only case in which you have spherical symmetry. So really A is a measure of spherical symmetry. So we don't really have much control over it. I mean, obviously you can play around with some transformations, but you're not going to transform your target distribution to be spherical spectrum. Right. So A is intrinsically going to be a limiting factor, but B and C are things that you can.
So in this model, B and C correspond to where you place. That's B.
Yes.
And so C is the size.
Yes.
Got it. Okay.
Yeah. And if your density is reasonably spherical symmetric, and A is quite close to 1, and you've got massive amount of gain. And if it's not, then there's a limited amount of gain, but you can still get some. Oh, sorry.
Is E effective upon 1 over T?
B. Well, so this is these are one-dimensional quantities. So I mean, you'd want to be estimating the mean of every component. So these don't really. If you had a sort of a pilot sample, which really was from the distribution, then you'd want to be able to estimate. I mean, you should be able to estimate this reasonably well, right? So, but they're just one-dimensional quantities.
How would you estimate mu?
Sum them all up. I'm not saying I shouldn't trivialize it. It's not easy, but and obviously you do need a pilot sample for doing that. But I mean, I think we would advocate using adaptive approaches for this, right? So you move your sphere around. We've got your spheres here. Basically, you iterate the algorithm. You estimate these things. You move the sphere around, and you try to prove things. We're only just starting to do that, to be honest. I think it's fair to say, but it seems a lot of kind of scope for improvement. And the same thing for this. I mean, because this lambda really is a measure of variance. So you need to be able to sort of estimate that sort of on the fly and then adapt.
Okay, so the uniform and godicity result for the random walk metropolis of the sphere, it had this condition, which was polynomial tail on pi, right?
Yes.
Which was the norm to the power d, roughly, if I remember correctly.
Yes, exactly.
So this essentially says how much mass, when you do your stereographic projection, how much mass goes close to the North Pole.
Yes. Yeah. And so it's exactly, I mean, so exactly what this quantity here is exactly what the density is on the sphere. Usually, we're expecting that backgrounds. Goes to infinity, you've got. I mean, if it does go to infinity, there's still hope, right? But you've got to construct a different algorithm, right? It's like any. I mean, the good thing about this is that you know that it can only go wrong at one point. Yes. And you know, if it can only go wrong, and you know where that point is, so you can construct algorithms to get around that. In principle, we haven't really worked on that yet. I mean, it would be a natural thing to do.
Is it possible? I mean, maybe I misunderstand this condition, but to sort of embed this RD to RD times something else, another Euclidean space on which you take some simple light tail distribution. I mean, I'm just trying to satisfy this condition by increasing D. You know what I mean? Increase D, and then you're below, and then you just take the first D components in the end. I mean, just.
That's nice. It's a nice idea. Yeah, I can see what you might be doing. Yeah. So you want to. Yeah, it feels unnatural, but it's a clever idea. I mean, it feels to me like something might go wrong, but I don't quite know what. Yeah, but it's a clever idea. Yes.
Oh, thank you very much, Gareth and both speakers.